Welcome to today's paper reading. Today's paper is titled, A Primer on the Inner Workings of Transformer-Based Language Models. This paper was published on the AR14 preprint by Javier Ferrando and colleagues from Universitat Politècnica de Catalunya and CLCG, University of Groningen. The rapid advancements in understanding advanced language models have underscored the necessity for a technical introduction to contextualize these insights. This primer focuses on the current techniques used to interpret the inner workings of transformer-based language models, particularly those with a generative decoder-only architecture. The paper presents a comprehensive overview of the known internal mechanisms of these models, highlighting connections across popular approaches and active research directions. Key techniques discussed include behavior localization, information decoding, and the discovery of inner behaviors such as the attention block, feed-forward block, and residual stream. Figure 1 provides a comprehensive overview of the survey, detailing the structure and content of the paper. Section 2 introduces the transformer language model, outlining its components and architecture. Sections 3 and 4 delve into the interpretability techniques employed to analyze the inner workings of these models, offering insights into how researchers understand and decode the information processed by these systems. Finally, Section 5 presents the known inner workings of transformer language models, summarizing the current understanding of their operational mechanisms. The introduction highlights the development and widespread use of transformer-based language models, such as those by Radford, Brown, and Hoffman. Understanding the inner mechanisms of these models is crucial for ensuring their safety, fairness, and for driving improvements. The NLP community has seen an increase in interpretability research, leading to new insights into model functioning. Existing surveys have covered various techniques in explainable AI and their applications in NLP, with a focus on both encoder-based models like BERT and decoder-only transformers. This work provides a technical introduction to interpretability techniques, categorizing approaches along two dimensions, localizing inputs or model components responsible for predictions, and decoding information stored in learned representations to understand its usage across network components. Autoregressive language models use the probability chain rule to decompose the probability distribution over a sequence into conditional distributions. These distributions are parameterized using a neural network optimized to maximize the likelihood of a training corpus. The transformer architecture, particularly the decoder-only variant, is widely adopted for this purpose due to its expressivity and scalability. Each transformer layer includes components such as layer normalization, which stabilizes training, the attention block, which contextualizes token representations, and the feed-forward network block, which processes intermediate representations. Figure 2 provides a detailed view of the unrolled transformer language model, focusing on the expanded attention and feed-forward network blocks. The figure highlights the model weights in gray and the residual stream states in green, offering a clear visual representation of these critical components. This visualization is based on figures from Ferrando and Voida, 2024, and Voida et al., 2023, and serves to illustrate the internal workings of the transformer architecture, particularly how the attention mechanism and feed-forward network interact with the residual stream states. Figure 3 illustrates the forward-pass decomposition in a simplified transformer language model. It highlights three key paths: the direct path, red, which connects the input embedding directly to the unembedding matrix, the full OV circuits, yellow, which traverse a single OV matrix, and the virtual attention heads, gray, which involve both attention heads in a V-composition. This decomposition is crucial for understanding the contributions of different components to the model's predictions. In this section, we delve into the localization of behavior within language models, focusing on identifying which elements in the forward pass are responsible for specific predictions. We explore two main types of methods: input attribution and model component attribution. Input attribution methods, such as gradient-based and perturbation-based approaches, estimate the contribution of input elements to model predictions. Model component attribution involves techniques like logit attribution and causal interventions to understand the role of various model components. Challenges such as gradient saturation and computational efficiency are addressed through methods like integrated gradients, and context mixing. Ecological validity is ensured by careful design of causal intervention experiments, avoiding unrealistic perturbations. These methods collectively aim to provide a comprehensive understanding of how different elements within a language model contribute to its predictions. Figure 4 illustrates three distinct methods for calculating the contributions of intertoken interactions, known as CI/J, within the context of attention heads. The first method highlights the limitation of relying solely on attention weights, which fails to consider the magnitude of the vectors they operate on. To address this, the second method incorporates the norm of the value-weighted or output-value-weighted vectors, denoted as xj. Lastly, the distance-based analysis method estimates the contributions of weighted vectors based on their proximity to the attention output. These methods collectively aim to provide a more comprehensive understanding of context mixing within attention mechanisms. Figure 5 illustrates the direct logit attributions, DLA, for the output token W in transformer models. It shows the DLA for various model components, A, an attention head at null, H, B, an intermediate representation XL-1 via an attention head, C, an FFN block, and D, a single neuron. The DLA quantifies the contribution of each component to the logit of the predicted token W, leveraging the linearity of the model's components. This analysis extends to direct logit difference attribution, DLDA, for contrastive explanations, highlighting which components promote one token over another. Figure 6 illustrates the process of activation resample patching. On the left, the FFN output activation from the forward pass with the source input X is shown. This activation is then placed in the forward pass with the target input X on the right, resulting in a prediction flip from Italy to France. This technique demonstrates how altering specific activations can significantly impact the model's predictions. Figure 7 illustrates the concept of distributed interchange interventions, subspace activation patching, on a one-dimensional subspace, represented by direction U on the left. This method allows for fine-grained intervention by replacing the orthogonal projection of activations. On the right, the figure shows a single-layer transformer, where path patching is used to replace the edges of different paths connecting model components. This technique enables the measurement of both direct and indirect effects of an attention head on the model's output, either directly or via the feed-forward network, FFN. Figure 8 illustrates a binary probe designed to predict the sentiment of input sentences, categorizing them as either positive, P, or negative, N. This binary linear classifier operates within a one-dimensional subspace defined by the direction U in the representation space. The probe's purpose is to assess how much sentiment information is encoded in the intermediate representations of the sentences. By training the classifier on sets of representations derived from positive and negative sentences, the probe evaluates its accuracy on a held-out set, providing insights into the sentiment information captured by the model's representations. Probing techniques are tools used to analyze the internal representations of neural networks. These techniques involve supervised models trained to predict input properties from the representations, aiming to assess how much information about the property is encoded. The linear representation hypothesis posits that features are encoded as linear subspaces of the representation space. This hypothesis is supported by examples like word2vec, which captures linear syntactic and semantic word relationships. Sparse autoencoders are used to disentangle features in superposition by reconstructing internal representations with sparsity. These autoencoders help in evaluating the sparsity of features and the quality of the reconstruction. Figure 9 illustrates the concept of feature directions in a two-dimensional space and the operation of a sparse autoencoder, SAE. On the left, it shows three scenarios. A. Features as directions not aligned with the standard basis, leading to polysemanticity. B. Features aligned with the standard basis, indicating monosemanticity. And C. More features than dimensions, resulting in superposition and inevitable polysemanticity. On the right, the figure depicts an SAE trained to reconstruct a model's internal representation C, with interpretable SAE features found in the rows of DEC. This setup helps in understanding how features are represented and how superposition can be managed through sparse autoencoders. Figure 10 presents two key visualizations. On the left, it showcases the SAE feature visualization on Neuronpedia, highlighting the promoted and suppressed tokens, feature density, logits distribution, and maximally activating examples of a name mover feature in GPT-2 Small. On the right, it illustrates the architecture of a gated sparse autoencoder, emphasizing the encoder weight sharing mechanism, which is crucial for decoupling feature magnitude estimation from feature detection. Figure 11 illustrates the process of multiplying an internal representation Z by the singular value decomposition, SVD, of a matrix W. On the left, the multiplication is shown as a sum of products of singular vectors and values. On the right, the top right singular vector V1 indicates the primary direction of transformation, which reveals the tokens the matrix interacts with most when projecting onto the vocabulary space. The input representation Z and the associated left singular vector U1 function as a query and a key, with V1 acting as the corresponding value. In this section, we delve into the discovered inner behaviors of transformer language models, LMs. We start by examining attention heads, which can exhibit interpretable attention weights patterns, have QK and OV circuits that are meaningful, and serve specialized functions such as positional, subword joiner, syntactic, and duplicate token heads. Moving on to feed-forward networks, we discuss the behavior of neurons, highlighting their input and output characteristics, the presence of polysemantic neurons, and the universality of neuron features across different models. Finally, we explore the residual stream, where we address the uncertainty in feature encoding, the identification of outlier dimensions, and the use of sparse autoencoders, SAEs, to interpret these features. These insights collectively enhance our understanding of the internal mechanisms driving transformer LMs. Figure 12 illustrates two key mechanisms within transformer LMs, the induction mechanism and the copy suppression mechanism. On the left, the induction mechanism shows how an early previous token head, PTH, writes information from token A into the residual stream of token B using the WOV matrix. This information is then read by a downstream induction head's WQK matrix, which attends to B and increases its likelihood for the next token prediction. On the right, the copy suppression mechanism demonstrates how a copy suppression head detects and suppresses the prediction of a token that is confidently predicted in the current residual stream, thereby improving model calibration. These mechanisms highlight specific behaviors of attention heads that are crucial for the model's performance and calibration. Figure 13 illustrates the attention sync mechanism in large language models. An attention head at a specific token, C, is shown to attend to the beginning of sequence, BOS, token. The OV, output value, circuit of this head compresses the BOS residual stream representation, resulting in a minimal update that leaves the residual stream of C largely unchanged. This mechanism is crucial for maintaining the integrity of the residual stream. Additionally, Cancetta, 2024, proposes that early feed-forward networks, FFNs, in models like Llama 2 write relevant information into a dark subspace within the BOS residual stream. This dark subspace allows subsequent attention heads to leverage this information without significantly altering the residual stream. Gurney et al., 2024, further identify specific neurons in the FFNs of the previous layer in GPT-2 models that regulate the degree to which the query attends to the BOS token. This control is depicted in orange in the figure, highlighting the intricate interplay between different layers and components in managing attention and information flow within the model. Figure 14 illustrates an example of the local context precedent feature identified in a sparse autoencoder, SAE, that has been trained to reconstruct the second layer residual stream of the GPT-2 small model. This feature is part of the SAE's capability to identify and promote specific tokens such as Obama, Bush, and Donald, which are associated with the concept of president. The SAE's ability to reconstruct and highlight these features provides insights into how the model processes and represents such high-level concepts within its residual stream. Figure 15 illustrates the simplified version of the indirect object identification (IOI) circuit in GPT-2 Small, as discovered by Wang et al., 2023a. The IOI task involves predicting the indirect object, Mary, In sentences like when Mary and John went to the store, John gave a drink to underscore underscore underscore. The circuit includes S-inhibition heads and name mover heads, which work together to signal duplicity and copy names, respectively. This setup ensures the correct prediction of the indirect object by modifying attention and copying signals in the residual stream. Figure 16 illustrates the simplified factual recall circuit within transformer-based language models. The circuit involves three main types of attention heads: subject heads, relation heads, and mixed heads. Subject heads are responsible for extracting attributes from the subject independently from the relation, ensuring that the subject's characteristics are accurately captured. Relation heads promote attributes without being causally dependent on the subject, allowing for the consideration of relational information that is not tied to specific subjects. Mixed heads generally favor the correct attribute and depend on both the subject and relation, combining the strengths of both types of heads to resolve the correct prediction. This combination of heads, each proposing different sets of attributes, together with the action of some downstream FFNs, enables the model to accurately recall factual information. This slide provides an overview of various tools designed to facilitate interpretability studies on transformer-based language models, LMs. We start with input attribution tools like CAPTM, which supports several gradient and perturbation-based methods for any PyTorch-based model. Moving on to component importance analysis, Transformer Lens is highlighted for its role in circuit discovery and causal interventions, balancing complexity with broad support for various pre-trained LM architectures. Lastly, visualization tools such as Birdwise, Expert, and Interpret are discussed for their capabilities in visualizing attention weights and activations within transformer-based LMs. Table 1 provides a comprehensive overview of the key variables and their definitions used throughout this work. It starts by defining the sequence length N and the vocabulary V. The table then delves into the model's dimensions, including the model dimension D, attention head dimension DH, and FFN dimension DFFN. Other important variables include the number of heads H, the number of layers L, and various representations within the residual stream and attention mechanisms. This table serves as a foundational reference for understanding the mathematical notation and definitions used in the analysis of transformer models. Thank you for watching.